Hey guys, welcome back. Today we're going to be discussing acid-base equilibration. So let's look at the problem. What is the pH of a solution of 25.00 milliliters of 3.5 molarity formic acid at its equivalence point when titrating with 1.2 molarity sodium hydroxide solution? And the Ka equals 1.8 times 10 to the negative 4. So the first thing we're going to want to do is use the dilution equation to solve for the volume of sodium hydroxide. So let's plug in the numbers. So, we plug in 3.5 molarity for molarity X and 25.00 milliliters for volume X. Now we can also plug in 1.2 molarity for molarity Y, leaving us with our unknown of volume Y, or the volume of sodium hydroxide. Now we can divide both sides by 1.2 molarity to find the volume. And we get about 72.92 milliliters. Now that we've solved for the volume of sodium hydroxide, let's take a look at the equation. Here's our titration equation. It's simply formic acid plus hydroxide yields the conjugate base, or formate, plus water. And you can find just about any titration equation by using the standard form. If you're titrating an acid, you'll take the acid plus hydroxide, and it will yield a base, or the conjugate base, which has one less hydrogen than the acid, plus water. Now that we have our equation, we need to solve for the amount of moles of the conjugate base. To start, let's look at mx, or the molarity of formic acid, which is just the moles of formic acid over the volume. If we multiply that number by the volume of formic acid, then we will receive the amount of moles of formic acid. And at the equivalence point, or the stoichiometric point, the moles of formic acid will be equal to the moles of the conjugate base. This means that we can take the molarity of formic acid, multiply it by the volume after converting it into liters, and finally, multiply it by a 1-to-1 ratio since we are at the equivalence point. And that will give us the amount of moles of conjugate base. Now that we have found the number of moles of conjugate base, we must convert this to molarity. We will divide the number of moles of conjugate base by the total volume, aka the volume of formic acid plus the volume of sodium hydroxide, which we solved for earlier. And we must convert this into liters before dividing, because molarity is the ratio of moles to liters. And this gives us about 0.89359 molarity of conjugate base. So here is an ice table representing the equation once the conjugate base is now equilibrating with water to reform the formic acid and hydroxide. This is just the reversed equation of the initial titration. Now, you might be asking, how do we fill out an ice table? Firstly, the I represents initial, and we now have the molarity of the conjugate base. And we can input that as our initial value for our conjugate base. We're not going to input any values for water since it's a liquid, and we don't include liquids in ice table. Now, for formic acid, at the initial stage of the reaction, or the I in ice table, we're going to have 0 because the reaction has a starting date. We'll have the same for hydroxide. The products are always 0 at the initial stage of the reaction because we haven't created anything. Now, for the C, or the change row of the ice table, we know that some amount of conjugate base is going to get consumed. So we're going to subtract X since we don't know that number yet. And we also know that some amount of formic acid is going to be created. So we're going to add X for both formic acid and hydroxide. The reason why we're able to use X for all three is because we know for every mole of conjugate base, there will be 1 mole of formic acid and 1 mole of hydroxide created. So the amount created will be X for both formic acid and hydroxide. Now, for the equilibrium row, we're just going to input the values as 0.89359 molarity minus X. And for the products, we're just going to have X for each. We're simply taking the initial row and adding the change row. Now you might be wondering, how can we find pH solely from this ice table? Well, first, we need to solve for Kb, because we are equilibrating a base in water. We can find Kb by utilizing this equation here. Ka multiplied by Kb will always equal Kw, and Kw is simply a constant. It is 1.0 times 10 to the negative 14. And we are provided with Ka in the question, where it states that Ka is equal to 1.8 times 10 to the negative 4. This means that we can just divide both sides of this equation by Ka, and we will be able to solve for Kb. And so we get for Kb equal to 5.56 times 10 to the negative 11. Now, how can we use Kb to solve for x in this ice table? Well, K is always equal to the products over the reactants. Now, what does this mean? This means that the Kb will be equal to the products, aka x times x, over the reactants, which is just 0.89359 molarity minus x. Now, we can do two things to make this a little more clean. First off, we can notate this as x squared. And secondly, we know that x is going to be incredibly close to 0, meaning that we're able to remove it from the denominator as it will not significantly affect our value. Note that we can only do this for the denominator and not the numerator. Now we can solve for x. And simply by multiplying both sides by 0.89359 molarity and square rooting both sides, we have solved for x, aka 7.05 times 10 to the negative 6th. We can now plug x in for our ice table, and now we can finally solve for pH using this equation. So pH is equal to 14 minus POH. And unfortunately, we do have hydroxide's value at equilibrium. This means that we can use this equation. So POH is simply the negative log of the concentration of OH minus at equilibrium, which we have already solved for. And since pH is just 14 minus the POH, we now can just plug this into our calculator and solve for pH. And so we get pH is approximately 8.85. Thanks for watching. Like and subscribe.